record so I can post this. So we're going over worksheet 22, which is a bit of old stuff. We're going to be reviewing these reactions a bunch to hopefully get you guys comfortable. So number one, we'll just draw all these molecules. And the question is just asking which of the leaving groups are best for an SN1 reaction. And I worded it like this, but I guess I'll ask now, like, is a leaving group that's good for an SN1 reaction generally also good for an SN2 reaction? Or are they exclusive to one or the other? So we'll talk about what makes a leaving group good, and then I'll explain the answer to my question that I might not have worded very well. Thank you for letting me know you're here. Okay, so plus sign on that, I guess. All right, so I guess first off, this structure here, top left, do you guys think this is a good or a bad leaving group or an SN1 reaction? Do we know what makes something good or bad at leaving? Good because of the positive charge. That's a big key of it. So it is good. And I guess I'll write down here, like, a good leaving group is good at stabilizing a negative charge. And it has to be good at that because when something leaves, it takes the electrons from the bond it had with carbon. So when it leaves, it's gonna look like that in terms of electron flow arrows. It's going to have an extra pair of electrons. When this thing, the first one, leaves, it has a positive charge, so it just becomes neutral. That's ethanol. It just leaves as an alcohol. And you should know that alcohols are stable. We've seen them used as solvents before. So this is perfectly fine leaving. So it stabilizes the negative charge because it had a positive charge to cancel it out in this case. Anything else that stabilizes a negative charge, like, you should recall from the beginning of the semester that the stronger an acid was, the weaker the conjugate base would be. So like hydrochloric acid and hydrobromic acid are strong acids. You should remember that from general chemistry. The conjugate base is the chloride ion or the bromide ion. So based on that is what comes from this. Is a Cl minus. Is this a strong or weak base? That's what comes from this bottom left. It's going to be a weak base because HCl is a strong acid. And something that is a weak base is weak because it's not very reactive. So the fact that it's not very reactive means it's stable, which means this is another good leaving group. Halogen is good at stabilizing a negative charge because it's a super weak base. It's basically not reactive. What about, thank you, what about the top right. Well, it's not top right on my worksheet, but the second one here on the top on the screen. Would this be good or bad at stabilizing a negative charge? I think it's not OTOS. OTOS has a aromatic ring somewhere. So let's draw what happens when this leaves. You get a negative charge here, and then the sulfur. So for something to stabilize negative charge, you just have to look at like reactivity and how stable the compound is. I understand it is probably hard to see at first glance. It's just kind of something you get used to over time. But okay. So if you have, yes, resonance, we have resonance here. So we can do that and push this up. So basically the negative charge can be on any of these oxygens, and then the double bonds can be between the other two. So there's at least 3 resonance forms, and that's a decent amount. And they all put negative charges on oxygen, which is an electronegative atom. So they're all pretty stable forms. So that is a finer detail you don't really have to worry about, but it just means that this is very good at stabilizing a negative charge because there's resonance and all the forms are happy. So this is good at stabilizing the negative charge it gets when it leaves. So is it a good or bad leaving group? It's going to be good. It's just going off of the definition down here. I described why it's good at stabilizing a negative charge because of resonance stabilizing it. So it's a good leaving group because it stabilizes the negative charge. If there are any questions about this, please stop me because I don't know if he would ask you a question where he shows something like this that you've never seen before, but you should, like, if he did end up asking something like this, you should just draw the arrow as if the group leaves and then look for resonance to see if that stabilizes it, or if there's a positive charge, that's pretty good for stabilizing something. And then some common good leaving groups are halogens, the OTOS. That's mostly it, to be honest. You can convert the alcohols with some reagents. The best way to tell if a leaving group is good or not is to see what happens when it leaves. Yeah, that's if you want to logic it out instead of memorizing things, yes. And I always recommend that because I think it's easier. So like I was saying with the halogen, this is the conjugate base of a strong acid, so it's a super weak base. So weak base means it's not reactive, it's stable, it stabilizes the negative charge, so it's good. And then here it's positive when it's attached, so it's going to become neutral. Neutral things are fine. This is stable because of resonance. If we look at the OH here, that's going to lead to a hydroxide. And you should remember that hydroxide, like sodium hydroxide, is a strong acid. I mean, it's a strong base. So strong base means it's reactive, it's not stable. So it doesn't stabilize the negative charge. So OH is going to be a bad leaving group. And then similarly, NH2 minus is going to be what forms, and this is a relatively strong base, so it's also going to be a bad leaving group. if this was an NH3, then it would be positive, and then when it left, it would be neutral, so it would be fine. But because it's NH2, it's going to form a strong base, which is a bad leaving group. So I think there's a table or something that shows like the reactivity of the leaving groups. You could memorize that if you want to. And there's not that many, so it's not that bad. But I think understanding this idea is important because he might throw something like this you've never seen before, and you should be able to explain why it would be good or bad. So here I'm just drawing some nucleophiles. Oh, I didn't. I'm gonna go back because I brought up a question that I didn't answer. So the question for one was asking which of these is good for an SN1 reaction, but okay, maybe I should have put SN2, but like leaving groups are equally as good for SN1 and SN2 reactions because what makes a leaving group good is just stabilizing the negative charge. That doesn't matter what kind of mechanism it's doing. The only difference between SN1 and SN2 reactions is the hydroxide group can be a good leaving group because SN1 uses acidic nucleophiles usually. So that will protonate the alcohol to form water, which is positive, and then water is a good leaving group. So that's the only difference in leaving groups between SN1 and SN2, and that's something that you should recognize. Okay, number 2, now I'll draw nucleophiles. So this is asking which of these would be good for an SN1 and which would be good for an SN2 reaction. Do you guys recall what kinds of nucleophiles are good for what reactions? Strong what for SN2? Oh, strong nucleophile, yeah, okay. So strong nucleophile, and generally a strong nucleophile is also a strong base. There's one exception to that rule, and that's acetonitrile, yeah. Wait, no, S-cyanate group, which you might not know because you didn't have to memorize the pKs, but HCN is a strong acid, so its conjugate base is a weak base, but this is still a strong nucleophile. And then for SN1, you generally want weaker nucleophiles. And a lot of the time, that just involves neutral or acidic conditions. And you're getting close to the point you're going to discuss this in lecture, so I'll just explain now the reason you want to use weaker nucleophiles or acidic conditions to do an SN1 mechanism is because if you have like a tertiary leaving group and you used a strong nucleophile, like, you know, if it's tertiary, you can't do SN2 because you can't do a backside attack. But if you used a base, you would do any 2 reaction, which you learned about today. So instead of getting an SN1 reaction where you do substitution, you'd get elimination if you use the base. But if you use a weaker nucleophile or an acid, then you're not going to do E2. So that's the reason for the weaker nucleophile. Okay, so the question, is this good for SN1 or SN2? SN1, yes, and we can understand that because there are lone pairs on this, but it's a bit acidic because of the proton there, and it's generally a strong nucleophile is something that has a negative charge because it wants to get rid of the negative charge. I say it generally because this next example is a bit of an exception. Is an acetate ion good for SN1 or SN2? Is this a strong nucleophile? Is the acetate ion a strong nucleophile? No, it's not, yeah, because there's a resonance form here that stabilizes the negative charge, and because it's stable, it's not as reactive, so it's not a strong base or a strong nucleophile. So this is like the only exception to something having a negative charge being a bad or a weak nucleophile. At least the only one you're going to see on this test, more than likely, unless you see something else with resonance, but this is a common one. So because it's a weak nucleophile, it would be better for an SN1 reaction than an SN2. Oh, I forgot to draw one. I'll just put it here, I guess. Okay, so NH2 minus, is that going to be good for SN1 or SN2? This guy here. So SN2 strong base, yeah, Jared's correct. So if we see a negative charge, like I was saying, generally that means it's a strong nucleophile or a strong base. And that means it's good for SN2. Like I'm emphasizing, this is basically the only exception to that because of resonance. This is a weak nucleophile. But if you see a negative charge anywhere else, then it's going to be strong. Okay, what about this? It's just methanol. Is that a good nucleophile for SN1 or SN2? It will be good for SN1. We don't see a negative charge. And an alcohol is not the strongest of nucleophiles. And what about chloride ion? Is that going to be good for SN1 or SN2? I'm going to erase this. Okay, I do feel like this one is a bit more up to interpretation, but I feel like, I mean, it is the conjugate base of a strong acid, but a chloride ion can react by itself in something. So like if you reacted NaCl with like OTOS or something, this is probably gonna substitute for the OTOS. So I argue, I guess it could go both ways, but if we were using HCl, I'd say it's good for SN1 because that's an acid, just like this is kind of an acid, and so is this. But because I put Cl minus, that's like saying it's NaCl, and I would probably do an SN2 because of the negative charge, making it better at being a nucleophile. I don't think he's going to ask a question that would be kind of confusing and up to interpretation like this. But like I was saying, the negative charge most of the time means that it's going to be a strong base besides resonance stabilization. I know that's a bit confusing and contradictory, but Bochem has contradictory stuff like this. I can't really change it. So There was a point I wanted to make, but I forgot. I'll just move on. But hopefully that all made sense. So that doesn't look amazing. Did he tell you guys about the Zaitsev product of an elimination reaction? Do you know what that is? Okay, can somebody tell me what the Zaitsev product is? Like a generalized definition for what it's referring to, or an analogy to reactions we've seen in the past, and a term we used before. Okay, I'll more substituted, and yeah, so more substituted product favored. So the more substituted product is the major product generally. Or I should put major product. And what, oh geez, major. Sorry, my brain is all over the place. The analogy to another kind of reaction, you should hopefully remember Markovnikov's rule for the more substituted product forming. And there were also anti-Markovnikov reactions, just like their anti-Zaitsev reactions, which are called Hoffman, I think. But these two are like the same rule, just Markovnikov is for adding things, while Zaitsev is an elimination reaction rule, but they're both more substituted. That's what they're referring to. Okay, so in order to do an elimination reaction, I should have put the mechanism question before this one, but you have a leaving group and you need a hydrogen to be one carbon away from the leaving group to form a double bond between the carbon and the hydrogen. I mean, between the two carbons with that neighboring hydrogen. So there's one at both of these positions, so we can form a double bond going both ways. This is one, and then this is another. And we can't form any other double bond products from this because these are the only two neighboring carbons to that leaving group there. So, like, if you were asked this question on a test, you would be wrong if you drew this because the halogen was not here or here, so we couldn't form a double bond here. So that's a no-no. Which one of these two is the Zaitsev product? The one on the left or the one on the right? Right, yeah. Because this one has 1, 2, 3 substituents, so it's tri-substituted. This one only has one substituent, so it's mono-substituted. So this has more substituents, and it's the Zaitsev product. So if you're not specifically told to, well, you should probably ask him to make sure this is how you should do it. But when I took the class, if you're not specifically told what products to draw, we were usually expected to draw all the expected products and then identify the major product, which is the Zaitsev product here. But this is going to form in a decent amount too. So it's just good to know which one you're mainly going to see, but both are going to be there. But again, you might want to ask him because I didn't take the class with Derwin. I don't know exactly what he wants. Okay, so we have a leaving group here, and to the right there's a hydrogen on the neighboring carbon, and to the left there's also a hydrogen on the neighboring carbon. So we can get a double bond going both ways. So we can get a double bond going here, or a double bond going here. We couldn't get it here or here. Those are the only other two positions. So I'm just pointing out, like, don't draw those because the halogen wasn't over there. So we couldn't do that. Okay, which one of these two is the Zaitsev product, the top or the bottom? Top, yes. And we can figure that out by looking at the substitution. This one has 1, 2, 3 substituents, so it's tri-substituted. And then the bottom one has 2 substituents, so it's di-substituted. So 3 versus 2, that has more. This is the Zaitsev product. And that's what you would mainly see. Oh, I'm getting ahead of myself. So again, on the neighboring carbon, there's a hydrogen on the left, and then there's a hydrogen on the right, so we can form double bonds going both ways. And this need for a neighboring hydrogen isn't a characteristic of SN1 or SN2 reactions, it's just a characteristic of elimination reactions, but it's an important characteristic, as we'll see shortly. So because there's neighboring hydrogens both ways, we can form this, and we can form this. Which one of these two is the Zaitsev product? Top or bottom? Top again, yeah. Again, this is tri-substituted because there's 3 substituents on this one, and then this one is only mono. So 3 versus 1 makes this the Zaitsev product. So that's that. So this is very similar to the last one, but we have a methyl group here. So this carbon here has 1, 2, 3, 4 bonds shown. That means there's no hydrogens on it. So because there's no hydrogens, we can't draw this. And that can't form because there's no hydrogens, but also if you ended up drawing that because you didn't recognize that there were no hydrogens, you would hopefully notice that this carbon here has 2 bonds, 3 to double bond, 3, 4, 5. That violates its octet, so this doesn't exist. But we still have a hydrogen over here. So we can form that, and that's all that forms. So this is the Zaitsev product because it's the only product. So hopefully this example just brings to your attention that you should pay attention to what's neighboring and not just jump to the conclusion that the thing with the most substituents will lead to the Zaitsev product, because there's a chance that there's too many substituents and you can't even form a double bond. So double check is the key there. Okay, so here we're just showing the mechanism this is going to go through. So what's the, well, first of all, if we want to figure out what the mechanism is going to look like, we have to determine what the reaction is. We haven't even covered E1, but you should recognize from these conditions what kind of reaction this is going to be. What is it going to follow? What kind of mechanism? So we have a tertiary we do have a tertiary substrate, so that makes it look like it's going to be SN1. But remember, I pointed out earlier, we used weak nucleophiles and acidic conditions to favor SN1 to avoid competing elimination reactions. NaOET isn't a weak nucleophile, it's a pretty strong one. This is a protic solvent that favors SN1, but the solvent is like it's basically the thing that matters the least. It's mostly just there. And for E2, it's okay with a polar protic solvent, as far as I know, at least. So what's important is the nucleophile here is a strong nucleophile. So we have a strong nucleophile, not a weak nucleophile. That's going to favor an E2 or an SN2, but we can't do SN2 here. So because it's tertiary and there's a strong nucleophile, it's E2. That's the reasoning I would go through. If you see tertiary, you should think E2 or SN1 or E1, and then look at the nucleophile. And if it would be a weak nucleophile, it would have been SN1. But because it's strong, it's going to do E2. So what's the first step in an E2 mechanism? You guys should have learned this today. Alpha position, that's one carbon away. Yeah, I didn't learn that. I didn't learn that terminology when I took the class, but that's cool. He brought that up. So we forms the double bond going this way. So the alpha position is going to be one away from the leaving group. It's going to be this carbon to the right. And the base is an OET minus. So, oh, another thing I didn't really know, like I was emphasizing look for negative charges when you're looking for a strong nucleophile. There's no negative charge here, but the sodium is just a counter ion for the negative charge on the oxygen. So that's why it's a strong nucleophile, even though it doesn't look like it at first glance. So that's just something to be mindful of. So this is the hydrogen the base is going to attack. And then what happens? If this is all that happens, the hydrogen would be bound to the oxygen here and the carbon there, and its octet would be broken. How does the double bond form? So we basically just, it might be hard to put in the text, so that's okay. We basically just take the electrons from the carbon-hydrogen bond and we use it to form the double bond. And then if this is all we did, then this carbon here would have 1, 2, 3, 4, 5 bonds because of the double bond. So the leaving group has to leave. And that's it. It all happens in one step. There's no intermediate. The base just takes a neighboring proton the electrons from the carbon-hydrogen bond basically act as a nucleophile to form a double bond, and then that kicks out the leaving group, and that all happens at one time. So this is what the E2 mechanism looks like all the time. It doesn't matter what the nucleophile it is, it doesn't matter what the leaving group or substrate is, it always looks like this. So I'm not going to write out that entire statement, but number 5 is saying true or false. The 2 in E2 tells us that the mechanism has 2 steps and passes through an intermediate. Is that true? False? Yeah, I kind of gave it away, but it's false. What does that 2 stand for? Yeah, it's a bimolecular elimination reaction. And it's bimolecular for the same reasoning as SN2 was bimolecular nucleophilic substitution, because the rate law depends on both the substrate and the nucleophile. It depends on 2 things, so it's bimolecular. And it depends on both because everything happens at the same time, so because everything happens at the same time, that's another thing. It's only 1 step. There's no intermediate. So that part of the statement was false, along with what the 2 stood for being false. And I'm pointing this out again, even though I asked the same question with SN2, because this is an extremely common mistake. People think E2 is the one that has 2 steps, and SN2 is the one that has 2 steps and passes through an intermediate. That's not what the 2 stands for. It stands for bimolecular, because it depends on 2 things. So the one with the 2 has 1 step, and the one with the 1 has 2 steps. But if you remember what the 2 is referring to, then that won't confuse you. That's why I'm drilling it into your heads. So hopefully this makes sense. Okay, so yes, that's number 5. Number 6 is another one, true, false. Each reactions require syn paraplanar geometry in order to proceed. Is that true? It looked like he covered it in his lecture notes. So we're getting a mixed response. It's important to, like, so I've said syn paraplanar. It requires like a paraplanar conformation with like the orbitals being with the same orientation. But syn means they're on the same side versus, yeah, they're anti is they're on opposite sides. And I can go ahead and draw a representation. I don't know if he showed it in class, but I'll just put, okay, that's good. So like this would be an anti-paraplanar geometry. And you can see like the hydrogen is pointing up, and this is what would be taken by a base, and then the leaving group is pointing down. They're pointing in opposite directions. So that's anti. And then syn would be like this. Okay, I flipped the molecule around, but that doesn't really matter. So you can see that they're eclipsing each other and they're pointing in the same direction. And just like SN2 was a backside attack, E2 kind of follows the same methodology in that like the nucleophile, the base, take hydroxide, it attacks a proton from the opposite side of the molecule from the leaving group, just like SN2 denucleophile attacks the carbon from the back side from where the leaving group was. And then this is it's kind of hard to draw in this orientation, but it would look something like that, and then the leaving group would leave. But the base came from the opposite side, it came like from the top, compared to the leaving group being on the bottom. So this is anti-paraplanar. It's very similar to the backside attack, so hopefully it's easy-ish to remember that anti-paraplanar looks like this. And the statement was false because I said sin. So don't just see the word paraplanar and immediately remember that that was related to the requirements. The sin is also important. Okay, and number 7 is just figuring out what the products of these reactions will be. And to do that, we'll have to determine what the mechanisms are for some of them. Okay. So what mechanism do you guys think this would follow? First thing we should consider is the substrate, the leaving group, SN2, yeah, so we'll put that and then we can explain it. So the substrate here is secondary because it's bonded to 2 other carbons. If it's secondary, it could be SN1 or SN2 or E2 or E1, like it could be any of them because secondary can go either way. So we have to look at other factors. Our nucleophile here, sodium hydroxide, is that a strong or a weak nucleophile? So you might think at first glance that it's weak because you don't see a negative charge that I was emphasizing, but again, sodium's a counterion, so there is a negative charge on the OH, and negative charges usually mean strong nucleophile, and hydroxide is a strong nucleophile, so it's a strong nucleophile. And then this MECN is acetonitrile. Is this a aprotic or a protic solvent? So Me is just a CH3 bonded to a CN. Is this protic or aprotic? In order to be protic, there should be a hydrogen bonded to a oxygen, nitrogen, or sulfur. And if we look at the structure, we can see that we don't have a hydrogen on the only nitrogen in here, so it's an aprotic solvent. So strong nucleophile and aprotic solvent are both conditions that are good for an SN2 reaction. So this would do an SN2 reaction. It might also do E2, but I think around the end of the chapter, he'll explain more rules for figuring out exactly when different things will happen. So We won't worry about that too much. I'm going to say that both would probably happen, but we're just going to go with SN2 here. And you should note that I started with a wedge and the product has a dash, so the stereochemistry inverted. And that is a characteristic of SN2 reactions. The stereochemistry inverts. And it does that because we're doing a backside attack. So it's as if this is on the top and then that is on the bottom now. Kind of similar to the anti-paraplanar thing with U2. Alrighty there. Doesn't look great. Is this going to be an SN1 or an SN2 reaction? Why do you think no reaction? Are you thinking that because this carbon free prime? What does free prime mean? Are you talking about tertiary? So that is a tertiary position, but I think you're thinking of if I drew this, then the carbon right next to it has basically a terbutyl on it, and the carbon is quaternary. And then that makes it difficult to do a backside attack because like the methyl group kind of gets in the way along with everything else getting in the way. I'm pretty sure that's the idea you were referring to. But here, like you pointed out, this is tertiary. So, I mean, this probably would be slowed down for an SN2 reaction, and you said no reaction, so I'm guessing you recognized that the positive charge and negative charge, this is, oh, okay. Yeah, so this would probably be slower, but it could happen. And this is also benzoic position, so benzoic and allylic are generally okay for SN1 or SN2. SN1 should make sense because it goes for a cation, and SN2, the book didn't seem to explain it, but it does say that benzoic positions are still good for SN2. So this is a secondary substrate that could go either way, but the nucleophile is negative and it's a strong base, so it's a strong nucleophile. And then DMSO is what kind of, well, that's what we're getting towards. So strong nucleophile, what kind of solvent is this? It's okay. Yeah, DMSO is an aprotic solvent. And again, don't memorize the structure, but this is a weird abbreviation, so you can remember that the weird abbreviations are usually aprotic. So strong nucleophile and aprotic solvent are factors that favor an SN2 reaction. Again, this could probably do E2 as well, but we're just gonna go with SN2 for now. So because it's SN2, what's gonna happen to the stereochemistry? We're adding the SH, but is it gonna be a dash or a wedge? Yep, it's gonna be a wedge. I knew what you meant. Because stereochemistry inverts when we do SN2. Okay. So what kind of mechanism do you guys think this will be? First thing we always consider is the substrate. This is tertiary because the leaving group carbon is bonded to 3 other carbons. So that looks like it's going to favor SN1 and E1, but if we also look at the nucleophile, what kind of nucleophile is this, strong or weak? Yep, it's a strong nucleophile. Again, there's no negative charge shown here, but that's because we have sodium masking it. It's a strong nucleophile. Solvent doesn't really matter, but it's the same solvent from the last part. It's aprotic. So this isn't going to do an SN2 reaction, even though these favor, like these conditions could do an SN2 reaction. It won't because it's a tertiary position, but we can do an elimination reaction because we have a strong nucleophile, and tertiary position is fine for an E2 reaction. So that's what's going to happen. It's going to be an E2 reaction. So we're going to form that double bond, and we're probably going to get a mixture of products. So like I was saying, it's generally a good idea to draw everything unless he tells you specifically he doesn't want it. Which one of these is going to be the major product? Top, yes. They look pretty similar, but this one has 3 substituents. Let's try versus this being di-substituted, so that has more substituents, so it's going to be the major product. Okay. Like I always say, stop me if you have a question, but otherwise I'll assume it's making sense. Okay, what kind of mechanism is this going to do? SN1, yes. And that is because we have a secondary position, so it could go either way. What kind of nucleophile is this? Strong or weak? Weak, yes. And then we have water as our solvent. Is that protic or aprotic? It's a polar protic solvent, so weak nucleophile and polar protic solvents are both things that factor in SN1 mechanism. So I didn't give stereochemistry in this problem, but let's just say that I did. Is this, well, it's not going to be chlorine anymore. Is that correct? No, it's not correct. So I don't have this on my answer key, and it's not something I brought up with you guys last time, but when you do an SN1 reaction, well, I pointed out that the carbocation intermediate is sp2 hybridized, so it's flat. So how do you know which atoms get bonded to the carbon? Is it the most electronegative? That's a way of looking at it. Generally, there's only going to be one thing that could potentially bond because SN stands for nucleophilic substitution. So we're substituting a nucleophile. Something that's a nucleophile is something that has lone pairs. So it's the thing with the lone pair that attaches. So like for OET, which is the equivalent to this, the oxygen is the thing with the negative charge with the lone pairs. With SH, the sulfur has lone pairs. So it just depends on what has lone pairs. And usually we're either looking at like carbon. Okay, so the only thing I want to point out here, because yes, normally it is the most electronegative thing, but this, the negative charge is not on the nitrogen, it's on the carbon. If you do the Lewis dot structure for this correctly, you'll see that there's a lone pair that ends up being on carbon. So it's this lone pair that is what's used as a nucleophile. So if we reacted this with the chlorine here, which would make it an SN2 reaction, but just to show you, it's the carbon that attaches, not the nitrogen. So don't remember that the most electronegative atom is the thing that attaches. Remember that it's the thing with, I guess, the most nucleophilic lone pair is the thing that's going to attach. Does that make sense? Okay, good. So yeah, back to what I was saying. Carbocation intermediate sp2 hybridized, it's flat, the nucleophile can attack from the top or bottom. So it's going to form like a 50-50 mixture of dash and wedge. And I didn't show this to you guys on Tuesday. I showed it to my other session, but you can just draw a line, but a better way to show it is with this. Well, it shouldn't be connected directly, but oh, whatever. It's like a spaghetti bond or a squiggly line. That's just to indicate that there's a 50-50 mixture of the dash and the wedge. I think that's a better way of showing it than just drawing this, like just a line. Doing the squiggly line is usually better. If you didn't cover this in class, then it probably doesn't matter, but this is technically the more correct way of showing it. But if you weren't given stereochemistry, like we weren't in the question, then it wouldn't necessarily matter. And you haven't gotten to E1 yet, but I'm gonna go ahead and spoil something for you. The conditions for E1 are legit exactly the same as they are for SN1. So if you have an SN1 reaction occur, pretty much all the time, you're also going to have an E1 reaction occur. The only reason it wouldn't happen is if you didn't have a neighboring hydrogen to do elimination with, because it still requires a neighboring hydrogen. But unless that's the case, you're going to have elimination reactions occur. So this is the SN1 product, but on top of this forming, we'd also get an elimination product, which would probably be this, because this is the more substituted product versus this. So we'd probably see all three, but mostly these first two I drew because this forms from SN1 and this is the major alkene product. And you'll cover that in lecture, but it's just the exact same conditions as SN1. So that's not too big of a leap in logic, I think. So number 8 is a bit of synthesis questions, which is gonna kind of go back to some stuff that's not gonna be on your next test, but it will be on the final, at least to some extent. These questions will, and the organo-copper coupling will come up at least a little bit probably. But when I do the multiple arrows. I did this once before. It just means that it's going to take at least 2 steps. It's not just one reaction to get to the product. And this question is specifically saying to use organocopper coupling reactions. So that's the thing with like R2CuLi and an ether solvent. And then you attach R to where there is a leaving group, a halogen usually. So you should notice that we added a methyl group here. So like I was just saying, we're substituting R for a halogen, so like an immediate precursor to this substrate here. And when you do synthesis problems, you should generally work backwards. But an immediate precursor to that guy would be something with a halogen on that spot where the carbon bond is formed. And we're adding a methyl group there, so it's gonna be like a CH3. There's 2 of them. This is R, and that thing I was just showing, CH32CuLi-THF. That's going to form that methyl. That's going to add that methyl group where the halogen is. And now we have to form some sort of intermediate between this and that, obviously. What reaction do you guys know that we can use to add a halogen to a position that's right next to a double bond? That's kind of the hint. This is an allylic position, and we're adding a halogen to the allylic position. NBS and what? Oh, I guess it just goes straight there. Because there are 2 different reactions we've done with NBS. So it's important to know which one. Remember a while ago when we were doing alkene reactions, there was NBS and water. And that would do this. That's not what we want. We don't want to add a hydroxyl and a bromine, and we also still have the double bond here. That's okay, it's just, I'm pointing this out because it'll be relevant on your final at the very least. You have to know that there's 2 different NBS reactions and there's a very big difference between them. So that's one of them. This reaction where we add the halogen to the allylic position, it's a radical reaction. So if you just remember NBS and HNu, that stands for light, that's basically good enough. The solvent is this, at least that's what it is in the book. Apparently we don't really use this shit anymore, but I guess the book's not up to date. So yeah, just NBS and light would probably be good enough. And we use light for radical reactions, like I said. So if you remember the mechanism for this is a radical mechanism, you should hopefully recall that light is the secondary thing involved here. Okay, so that puts a halogen at the allylic position, and then we have the organometallic coupling, adding the methyl group. Are you asking about like this allylic radical reaction? The last step. So are you asking like, could we have like the bromine going to the methyl? Yeah, this would be fine as well. Just I don't know if we can do the allylic halogenation with Cl2. I'm assuming we can. It wouldn't really make sense if we couldn't. but I've only ever seen the allylic halogenation done with NBS and light and tetrachloromethane. So that's why I drew this with a bromine, because it was going to come from this reaction. But you could definitely take this substrate and do that, and it would do the same thing. It just has to be an alkyl halide. So it could be chlorine, bromine, or iodine, but any of these would work with this to get to that product. Okay. Hopefully that answered your question. I didn't ask before I moved on, but okay. So again, we're using the same general reaction, the organometallic coupling. So like we're gonna have an alkyl halide and it's gonna react with something it's gonna react with the copper complex to form carbon-carbon bonds. So based on that, an immediate precursor to this, based on what we're starting with at least, like it could be this. There's a halogen where we're adding the carbon chain. It could be chlorine, iodine, bromine, just it has to be a halogen. And then we're adding free carbons here. So we're adding the propyl group. So I'm just gonna you could write out the like CH3, CH2, CH2, and then put 2 if you want, but this is another way you can show it. I put in parentheses the propyl group, and then I put the line out to show that it's bonded to the copper, and there's 2 of them. So that will react with the halogen to add the propyl group there. And now how can we get from this double bond to a halogen on this position? This is going all the way back to alkene reactions, so if nobody remembers, that's okay, but this will be relevant for the final. Yeah, HX in general is going to add the halogen to the Markovnikov position. And the Markovnikov position is that one because it's secondary versus primary. So we can use HCl to get the halogen attached there. And then we do the coupling to get that product. So most synthesis problems you're gonna see, well, I don't know if they're gonna come up on your tests, but you'll see them eventually. They usually don't tell you like use this kind of reaction as a step if it comes up on a test. You just have to know that's the reaction you're gonna be using. But this is good practice. Still. Okay, so again, we're using the same kinds of reactions. So an immediate precursor to this is going to be something that has a halogen on that position we formed new carbon-carbon bond on. Let's just say it's Br for this one. It could be Cl or iodine, but we'll keep it with bromine. And the reaction is going to involve just a cyclopentyl group. There's going to be 2 of them bonded to copper lithium complex, and it's going to be done in ether. So like pretty much anything could be attached to this copper lithium complex and react with an alkyl halide, and it'll work. So there's not really a limit on this. That's just something to keep in mind. There are usually limitations on reactions like this, but this one doesn't have that many. Okay, so it's not really obvious what the immediate precursor to this would be, like going backwards from this step, I think. So sometimes it's good to think going from the starts to try to get to there somehow. So um, on this double bond, we have a tertiary position and a secondary position. And you should notice we have the bromine on this position, which is secondary. Is that the Markovnikov or the anti-Markovnikov spot of this double bond? Anti-Markovnikov, yes. So we want to do a reaction that adds something to the anti-Markovnikov spot. Yeah. So if we added the bromine to the tertiary position, we could have just used HBr like we did before. But because we have to add to the anti-Markovnikov spot, there's only one reaction we know for this, and that's the BH-free reaction. It's 2 steps. That's going to put an alcohol on that anti-Markovnikov position, so we're not quite there yet. But now, how can we convert this alcohol to a bromine? Yep, that's one thing we can do, PBr free and ether. There's two things we can do to convert an alcohol to bromine. Because this is secondary, both of them will work, but I think PBr free is a little better for this particular reaction. It wouldn't matter on your test, but the other one is just HBr, CHF. That works too. The PBr free is an SN2 reaction. HBr is SN1 because it's secondary, they both work. And those are the free steps to do that. And last one. I'm probably going to go a minute over. I am sorry. So sorry. Is that enough? No, one more. Okay. So I'm just, I made an adaptation of a problem in the book to do this, and I remember being confused by the solution in the solutions manual because it took a slightly different path. So I'm gonna move forward from this one just because I guess it's kind of relevant for showing you guys. Those copper complexes are called Gilman's reagents, and this problem is basically just saying like we're gonna form a Gilman reagent from this and then react it with an alkyl halide. So to form a Gilman reagent, you take an alkyl halide and you react it with lithium and pentane can just be a solvent. It is just a solvent. And that's going to lead to this forming. And then once you have the lithium bounds, the next step is reacting it with copper iodide in an ether solvent. And this might seem like it's coming out of nowhere, but unless you're explicitly told like you only have one equivalent of this or one equivalent, you can assume you have excess. So because we have excess, we can say we have at least two of these. So this is, it's just like writing this as a reagent on top of an arrow. So this process is just showing how we would form this Gilman reagent. You take an alkyl halide, you react it with lithium, and then you react it with copper iodide, and you form a Gilman reagent. And then that reacts with another alkyl halide to form carbon-carbon bonds. So Gilman reagents are formed from alkyl halides and react with alkyl halides, which is a bit confusing, but that just is what it is. So this is going to then, there's only one step left. It's just reacting with, we should count our carbons. So we have 3 here, and we have 4, 5, 6, 7, 8, 9 here. So we're going to want to add 5 carbons. So just 2, 3, 4, 5. So this Gilman reagent is reacting with that. Now this is the reagent and that's the substrate, but it's the same exact reaction. So we're just adding like these 3 carbons to this, these 5. Wait, I should have one more. That's my bad. It should be 6. It should look like this because we have 3 and we end up with 9. Yeah, so I made a mistake, but I counted my carbons and I got it, so it could, but I think the book just wanted to make an example of how you would form a Gilman reagent. When I took the class, I wasn't expected to worry about forming the Gilman reagents. We were always just told like you could just assume you made it elsewhere, like we did in the other problems. We just used it as a reagent, but the book wanted to make an example out of it. And I don't know what your professor expects, so he might expect you to know how to form Gilman reagents. But it's just this first step of lithium and then the second step of copper iodine. You might want to ask him if you should know that or not, or if it's not a big deal. No problem. That's everything on my worksheet. So you're welcome. We're gonna have a worksheet up by tomorrow for next Tuesday. They'll probably have E1 stuff. Thank you for coming.